previous video that's referenced in the description of this video, I went over how we develop the half-angle identities. Here we're going to do a couple more examples beyond what was done in that video. So what I've done is I've relisted the half-angle identities for the sine of half an angle, the cosine half an angle, and the tangent half of an angle in 3 different forms. In the previous video, I just developed how we got the tangent of half of an angle by taking the sine of the half of an angle divided by the cosine of half the angle and then simplifying. But there's other simplifications that can be done that will generate these other 2 forms. So depending on what you have as information and what it is that you're trying to find would kind of dictate which of these forms you would use. Now also recall that we do have the plus or minus in front of the radicals when we have a radical definition of the half-angle identity. And that plus or minus isn't where in an algebra setting we said that it would be either this answer or that answer. This plus or minus is you have to choose the correct sign that the trig function acting on the half angle would have for where that half angle is located, whether it's a quadrant 1 angle, whether it's a quadrant 2 angle, quadrant 3, or quadrant 4. And then picking the correct sign to go along with whether that ratio of that trig function of that half angle should be positive or negative. So let's take that information and then look at these examples. So first of all, if it says to use the half-angle identity to find the exact value of the sine of 105 degrees. So with the exact value, I can't go to decimals unless it's a terminating decimal. So any of these answers that would have radicals in their expressions, I have to leave them in the simplified radical form. Now, 105 degrees is not one of our nice angles. And even if I found the reference angle for 105 degrees, it would not be one of our nice angles. So we're thinking, well, 105 degrees, how am I possibly going to find the exact value of the sine of 105 degrees? Well, we think back to our different trig identities that we've developed so far, and we look at the idea that if I took and thought of 105, what might it be related to something that would be a nice angle? And 105 degrees is exactly half of 210 degrees. And 210 degrees is an angle that has a reference angle that's one of our special angles. The reference angle for 210 degrees is 30 degrees. 30 degrees is a nice angle. So what I want to do here is I want to write this as the sine, still use the same trig function, and replace 105 degrees with its replacement that means the same thing as 105 degrees, but brings in an angle that I would be able to find the exact value of the trig ratio for. So I'm going to rewrite 105 degrees as 210 degrees divided by 2. So this is something that you just kind of have to practice looking at how you can think about these problems. In an earlier segment when we did the trig functions of sum or difference of 2 angles, sometimes we were looking at what 2 special angles could be added or subtracted to get the angle we're interested in. Here, it's one that we could do with our thinking about using our half-angle identities. Now, notice when I'm looking at the sine of something divided by 2, this 210 degree part in this problem, that plays the role of alpha from over there. So now this is going to be equal to, and I'm going to first put the plus or minus and then we'll decide what we need to have. So it's the square root of 1/2, so I'm just copying here, 1/2 times 1 minus the cosine of the alpha. So 1/2 times the quantity, 1 minus the cosine of 210 degrees. And I want to pick the plus or minus to be correct by where my half angle is. So where's 105 degrees? Well, 105 degrees is between 90 degrees and 180 degrees. And all of the angles that are in the span between 90 degrees and 180 degrees are in the second quadrant, and the sine of second quadrant angles, remember it's the vertical movement if we look at it in terms of our unit circle, so that would be up, so the sine of a second quadrant angle will be positive. So I'm going to pick the positive for that one. And now coming to the next line, it's the square root of 1/2 times 1 minus, now the cosine of 210 degrees. So think 210 degrees go to the nearest x-axis. The reference angle is 30 degrees. It's 210 is 30 degrees beyond 180. The cosine of 30 degrees is the square root of 3/2, but in the third quadrant it would be a negative square root of 3/2. And now simplifying further, this double negative will give me the square root of 1/2 times 1 plus the square root of 3/2. Building it down, common denominators, 1 could be written as 2/2. So that would be 2 plus the square root of 3 all over 2. And then 1/2 times 2 plus the square root of 3 all over 2 is 2 plus the square root of 3 all over 4. And then with radicals and radicals, I want to try to simplify this as much as I can. We'll break this up with the square root in the numerator over the square root in the denominator. So that's the square root of 2 plus the square root of 3, and that's all over the square root of 4. But the square root of 4 is 2. So we will just write this as the square root of 2 plus the square root of 3 all over 2. So that is our simplification for the sine of 105 degrees. I'm going to erase this, put this up here so that I have more room to write out the next few examples. Now let's look at example B, which is the cosine of pi over 12. To look at this one, I could try to see if there were any addition or subtraction of my special angles that would give me pi over 12. Or I could think, well, pi over 12, I can make an equivalent multiplication of 1/2 times pi over 6 that means the same thing as pi over 12. So if I took the cosine of 1/2 times pi over 6, I will get exactly the same thing as the cosine of pi over 12, and it involves one of my special angles with 1/2 of that, which means I can use the half angle identity. So now with this, it's the cosine of the half angle. So again, we're going to go to that formula, plus or minus the square root of 1/2 times 1 plus the cosine of what you're taking 1/2 of. So that's the pi over 6. Now the plus or minus is determined by what quadrant your half angle lives in. So this pi over 12 is in the first quadrant. So I'm going to use the positive sign for it. And then as we go through and look at this, we're able to then go 1/2 times 1 plus the cosine of pi over 6 is square root of 3/2. And then when I go through and simplify that, that's the square root of 1/2 times, well, one I can write as 2/2. So that gives me 2 plus the square root of 3 all over 2. And then when I multiply across the top and across the bottom, that gives me the square root of 2 plus the square root of 3 all over 4. And then when I take the square root of the top and the square root of the bottom, that gives me the square root of 2 plus the square root of 3 all over the square root of 4. Now the square root of 2 plus the square root of 3 doesn't simplify anymore. So I will just go ahead and write that up here. But the square root of 4 is 2. So I get the cosine of pi over 12 in its exact form is the square root of 2 plus the square root of 3 all over 2. Now we'll go and remove this part to make room to do the part C. Well, I can think of that as the tangent of 1/2 of 11 pi over 6. And I can use any of these three forms for the tangent of half of an angle. And I'm going to just choose to use the one that is the 2-term numerator and the 1-term denominator. So this is the same thing as 1 minus the cosine of the angle that you're taking half of. So that's the 11 pi over 6. Divided by the sine of 11 pi over 6. Now think 11 pi over 6 is a 4th quadrant angle with a reference angle of pi over 6. So to get to the 4th quadrant, the cosine is positive, the sine is negative. When I look at making these replacements then, it's 1 minus, well, the cosine of 11 pi over 6 is going to be the cosine of pi over 6, which is the square root of 3 over 2, and it's positive the square root of 3 over 2. And then the sine of 11 pi over 6, well, the sine of pi over 6 is a half, but 11 pi over 6 is a 4th quadrant angle, so my sine of 11 pi over 6 should be negative a half. Now I want to simplify this, and I have a fraction and a fraction, so I'll multiply the top and bottom by the lowest common denominator of these fraction pieces, which is going to be a lowest common denominator of 2. So I get 2 times 1 is 2, and then 2 times negative the square root of 3 over 2 gives me minus the square root of 3. And then in the denominator, 2 times negative a half is negative 1. And then when I take 2 minus the square root of 3 and divide it by negative 1, remember you can break those up as 2 separate fractions over a multi-term numerator and a monomial denominator. So I can think of this as negative 2 plus the square root of 3. So these are all the exact forms, and certainly these are the ways that you want to report them because it said exact value, so you can't go to your decimal approximation. You can, however, use your decimal approximations to see if you've got the right answer. So like in this first one, you can go to check your mode, check that you're in degree mode, take the sine of 105 degrees and just kind of jot it down on scratch paper. Remember, you don't want to report the decimal approximation. We're just going to see if we have the right answer. And then find your decimal approximation for the exact value you're going to report, the square root of 2 plus the square root of 3, and then all over 2. Make sure you enter it correctly, and then just compare those decimal approximations and make sure you have the same thing. And that way you can check it. Now when you go to part B and part C, make sure you go back to your mode key and you make sure that you're in radian mode before you get to the decimal approximation to compare with the decimal approximation of your exact value. And then also these first two came out to be exactly the same, just in happenstance of the questions that I chose to do as examples. It's not something that situationally will always occur. It occurred with referencing, with complementary stuff like that that's going on. But anyway, that's what you get for being able to find your trig functions of not special angles, but those angles that are half of special angles, and be able to still stay with an exact value for the trig ratios.